What are physicists' thoughts on the idea that there hasn't been any progress in physics since 1973? Why hasn't there been a major breakthrough in physics in the last 100? What are the most recent fundamental or theoretical physics discoveries that have led to significant change in society? I understand this could be a touchy, flamey subject, but it is very much not in my intention to be abrasive. Physics is stuck. Why are there no discoveries in physics nowadays? Why the foundations of physics have not progressed for 40 years. Is the stagnation of physics just temporary, or is it truly over? Who's killing physics? Has physics not progressed much since the 70s? Why has there been no progress in physics since 1973? Why isn't fundamental physics making great progress? When did fundamental physics progress go from a serious quest for truth to a financial racket? Physics has done very little for like 70 years, and it's disappointing. I think people need to think outside the box more.
Physics has done very little for like 70 years, and it's disappointing. I think people need to think outside the box more. Physics has done very little for like 70 years.
So, in 1953, one of the first ever computer simulations changed physics forever. The authors are Fermi, Pasta, Ulam, and Singu. It's called the FPAT experiment. They wanted to model a vibrating string, which has like simple equations of motion on the supercomputer just to test its abilities to solve a problem. And this computer was called Maniac, which is such a great name for a supercomputer. And Singu, she was the one that authored the program, put it in, and they expected the results to be ergodic. And an ergodic system is one that, if given infinite time, it will meet all of the possible states. So if you have a string vibrating, it should reach all of the possible states allowable on that length of string with that much tension or whatever. They expected if they run the simulation a bunch of times, they should meet that requirement, and it's just like, okay, simple check mark, we have an ergodic system. But it turns out that it's not ergodic, it's periodic. So the result was this: complicated nonlinear systems like a vibrating string with like some extra nonlinear terms do not produce ergodic results. Sometimes they are periodic. There's a lot of stuff there. Fermi died. The paper was released internally at Los Alamos after his death. They left off the fourth author, Mary Singu, who was the programmer, and showed them the interesting results. A lot of early programmers were, of course, women. They were all physicists, and yet for some reason they're not on the papers. That's so weird, but that's not the interesting bit. Don't worry, she gets credited later. But here's the thing. The interesting part is not that result. Although that result is interesting, the solution is solitons, and they found out in 1956. The real interesting thing, so computers immediately become recognized as this tool that can solve complicated math that we could not possibly do. So if you have a theoretical problem, you can use a computer to test that problem in ways you never could have before. And as a result, computer simulations are used everywhere all the time, in biology, in mathematics, in economics, everywhere all the time. Video games, computer animation, all that stuff is computer simulations. And because the computer simulation as a tool to solve physics problems just became immediately apparent as soon as we had the capability, all the physicists just jumped full feet into the development of better computers and better programming languages and all that stuff. Computer simulations, physics, neat. So that was in 1953. In 1954, I'm just kidding. I could literally do a list of all 70 years, and I wrote them all down because I thought that would be funny, but then I imagined editing that video. I'm not going to do that. I'm just going to do a top 10 list. You're in the top 10 list right now. Top 10 physics things in the last 70 years. That was number 1. It's according to me. Leave your top 10 list below. Number 2 is MRIs. Magnetic resonance imaging. It used to be called NMRI, and the N was for nuclear, but they were worried people wouldn't get in a device called nuclear magnetic resonance imaging. All right. MRI machines use these huge magnetic fields to polarize all of the protons in your body. And then they put a radio frequency through your body, which excites those protons a little bit and makes a change in that magnetic field. And then they rapidly turn off that frequency, and all of the protons go back to align with the magnetic field. And that change can be used to create an image of inside your body. This is a huge deal. The first MRI machines were used in the late 70s, and now they are just a fundamental part of medical treatment. Like, compare it to an X-ray where you get a dose of a harmful radiation that can cause cancer, or something like a biopsy where they're like, we need to check out this tissue. I guess we will cut you open and take a sample of it. An MRI is this pain-free, completely safe way to image different parts of the body. Freaking game changer. Can you imagine if you get headaches all the time and they're like, I guess our only option is to open your skull and look at your brain? No, MRIs. MRIs exist. Amazing. I just want to talk about space exploration for a minute. Like, humans went to the moon in 1969. That was a thing that happened. Okay, in 1977, we flung 2 probes out of the solar system, and in 2023, they are still sending us data. Oh my God. There have been robots on Mars doing experiments, making maps, taking data, sending it all back to us since 1997. In 2015, we drove the New Horizons telescope 3.2 billion with the B, miles to Pluto and took pictures of it. NASA's OSIRIS-REx mission spent 2 years in space until landing on an asteroid in 2018, mapping it, taking a sample, and bringing that sample back to Earth in September of 2023. We took a piece of an asteroid and now it's on Earth. An essential component of general relativity and a prediction made by Einstein is the existence of gravitational waves. In the late 1960s, Rainer Weiss and Kip Thorne independently designed these prototypes for giant interferometers that could detect gravitational waves. And then a whole lot of work was done. The very first implementation of LIGO was between 2002 and 2010, and it didn't get any results. It found no gravitational waves. And then they upgraded it, turned it on, and boom, 2016, gravitational wave detection. A component of general relativity is the existence of black holes and their event horizons. The Event Horizon Telescope is a collaboration of telescopes all over the world that, when combined, they have the angular resolution to observe the black holes at the center of our galaxy and Andromeda. Basically, together they make a telescope the size of the Earth. And in 2019, they published the very first images of the Milky Way's supermassive black hole. They took a picture of a black hole. I mean, that still happened. That's insane. Look at it. Oh my gosh. These 2 observations are experimental support of the very, very successful theory of general relativity, which we've been using for like 100 years. These predictions were made long ago. We finally have the equipment to be able to test them, and oh my gosh. So Bose-Einstein condensates were first proposed by Bose and then later by Einstein. They talked in papers and stuff in the early 1920s. It's a quantum mechanics idea. Bose-Einstein condensate was a theoretical idea about bosons in gas form, where if you cool them down to absolute zero or nearly absolute zero, most of the atoms in that gas will be able to occupy the lowest quantum mechanical energy state, meaning that most of the atoms in that gas all maintain the same identical quantum mechanical state, which allows you to test quantum mechanics on the macro scale. Because instead of having like one photon and you're trying to determine what state it's in, you have a little cup of gas that's all in the same state. It's macro because it's like that's a really big volume of a BEC, but you get me. You can test quantum mechanics in a way never before. And in 1995, the first Bose-Einstein condensate was made in a lab amazing. Since then, there's just been this huge explosion of like condensed matter theory, and tons of different Bose-Einstein condensates have been made all over the world. And by making different materials in this new state of matter, you can test all different types of quantum mechanical stuff and learn more about quantum mechanics, also a very successful theory of physics. Amazing. Condensed matter theory and experiment have absolutely kicked off in popularity since the 1990s. Like, everybody always talks about like high energy particle theory, but all of this stuff, you know, in my opinion, just in case you're thinking of going to graduate school in physics, is like happening here in condensed matter physics. It's an amazing achievement how much it's grown since the 1990s. So, the Higgs field was predicted, discovered, theoretically described in the 1960s as a way to form mass from the vacuum through spontaneous symmetry breaking. The Higgs mechanism requires something called the Higgs particle. The idea was that if we find the Higgs particle, we can prove that the Higgs mechanism is a thing, because that's what makes the particle, which will bolster the Standard Model, a very, very successful theory of physics that has been making predictions on particles like this for years and years and years. And in the 1980s, this was the biggest question in physics. It was like, okay, where's the Higgs? If we can't find the Higgs, the Standard Model doesn't work. And then, of course, in 2013, they found the Higgs particle. I was just a baby physicist in 2013. I had just started graduate school, but it was so exciting. I love to look at the pictures from all of the CERN confirmation stuff. It's really sweet and cute. The discovery and confirmation of the Higgs particle is kind of the last and most important piece of evidence supporting the Standard Model of physics as this very successful theory of physics. Physicists kind of have their hands in every single advancement in communication and data transmission. Think optical fibers, which were first built in 1965. You have data being transmitted through pulses of light through a cable that can span, oceans. Optical fibers reached the theoretical attenuation limit in 1970 with physicists working at Corning Glass Works, because the optical fibers are made of silica glass. Glass is important, actually. The first working integrated circuit was made by a physicist in 1958, and I would totally mention the importance of transistors here, but that was in the late 40s, and that's beyond our timeline of 70 years. So integrated circuits are what allow you to have any electronic device you've ever used in the past 70 years. Circuits used to be these huge devices, like if you've ever opened an old radio where you could remove a component, and now everything's just kind of tied into like a nice little printed surface that works perfectly and is amazing and small. Physicists have their hand in every development in communication and electronic devices for the last 70 years or so. I mentioned communication because the internet, the World Wide Web, was actually invented by a physicist at CERN in 1989. His name is Tim Berners-Lee. He made the first ever website. You are watching this video about physics because of physics. You are watching this video on the internet about physics because of physics. You are watching this video on a cell phone over a Wi-Fi network or a cellular network because physicists made those things. Physics has done a lot in the last 70 years. The foundations of physics were changed forever in 1957 when the authors of the BCS theory of superconductivity wrote their paper about the BCS, that's their names, theory of superconductivity. So MRI machines need these very large magnetic fields to polarize all the protons in your body, which means inside they have a superconducting electromagnet, which is just a coil of superconducting material made into a wire. And to make your MRI machine work, you need to send a huge current through that wire to make these huge magnetic fields. So if that coil has any resistance at all, you're gonna lose a huge amount of heat to that resistance. You're going to lose a huge amount of power to that resistance. So you'll have to keep adding more and more and more power through that to make the big magnetic field that you need to take the image that you need for medical purposes or whatever. The thing about superconductors, though, is that they, by definition, have no resistance. So you are allowed to make that big magnetic field and have no heat loss. Can you imagine if you had to get an MRI, but they were also like, yeah, this is going to be like 108 degrees in like 8 minutes, so we have to limit your time. It would be crazy. The reason MRIs work is because we have a superconducting material. That's so cool. I'm separating MRIs on my list because I just think that's such a beautiful application of physics, and like the field of medical physics has been exploding since then. But superconductors are an essential component to the MRI. Part of the reason this is such an active field of research is because right now our superconductors only work at very cold temperatures. For example, when you get that MRI, that electromagnet is surrounded by liquid helium, which is at like 4 degrees Kelvin. And so you might see in the news people talking about like room temperature superconductors. Oh my gosh, it's like every 3 years. And like, I mean, that's not going to pass the smell test. Like, don't fall for that every time, guys. Surely we would make it. It's fine. That's not the point of this video. Anyway, of course, though, if they were room temperature, it would have so many applications in like electronic devices, in quantum computers, in all of these things we want to build. If you have a room temperature superconductor, you don't have to worry about the size and the cost. You could have no resistance ever. Just like for fun, when people say room temperature superconductors, they're comparing it to the helium stuff that happens at like 4 Kelvin. And they have some stuff now with like liquid nitrogen, which is at 77 Kelvin, but they want to increase that to room temperature, which they call like 100 Kelvin. And I mean, that's kind of not room temperature. I don't know why they're doing that. Obviously, a huge active field of research that has had huge improvements since the 70s. And even small incremental like increases in the allowable temperature and stuff lead to huge benefits in applications. So this is a huge field of research happening now. So exciting. This is such a stupid idea for a video. I mean, lasers. The first laser was built in 1960 by Mayman. And lasers are everything. I made like a list and then I stopped because there were too many things. But lasers are essential for interferometry, spectroscopy, adaptive optics, laser heating, laser cooling, laser scanning, radar, particle accelerators, 2-photon excitation microscopy, cosmetic surgery, tattoo removal, eye surgery, laser surgery, cancer treatments, laser cutting, laser welding, optical fibers use lasers. Lasers have been used in every single fundamental physics experiment since the 1970s. Lasers are essential to physics, and it rivals like magnetic fields. Lasers. Lasers. If someone ever says this to you, just scream laser. Just scream laser and run away. I should give you an example. Like, say you're a physicist and you study quantum mechanics. You are doing a modern quantum mechanics experiment in a lab. You know that thing when you observe a particle and it collapses the wave function? To observe is to shine a laser at a thing. That's what we need. The lasers. Lasers are a big one. Lasers are important. Just look at this paper from 2017. This record-breaking paper. A laser with a line width of 10 millihertz. 10 millihertz. That's from 2017. That's insane. If you're studying quantum mechanics in a lab and you're observing things, you need a really stable, precise, exact laser. And these improvements in lasers have done crazy things in improving the accuracy of experimental physics results. By the way, I have seen some YouTube videos where people make lasers, and I love and support that, but sometimes they make these dye lasers, and they're called dye lasers because they're dye, but also because you die, because most of these are carcinogens, and they're toxic, and they're like actual carcinogens. It's not like Diet Coke in California, like it's an actual carcinogen, so don't make those. PSA, I'm not a doctor, but... In 1968, the duration of a second was defined to be this many vibrations of the unperturbed ground state hyperfine transition frequency of the cesium-133 atom. That's the literal definition of a second. Time has been redefined in physics in the last 70 years. These are called atomic clocks. Huge for physics. In the past, time was like defined by how much of a day it was, right? And that is not great if you're doing something like fundamental physics and you need to know within nanoseconds that something happened. If you need to know within picoseconds that something happened. So the development of atomic clocks is what allowed us to get more accurate experiments. And also, by the way, these are used for communication. International atomic time is defined and kept by over 450 atomic clocks all over the world. And these clocks communicate with not only the GPS satellites, but also all of the devices in your life that keep time for you. Time has never been more accurate than it is now. What's really interesting is that these clocks were set up in 1968, and early in the 1970s, they realized that these clocks were getting off of each other by like nanoseconds per year. And they realized when you have this accurate of a timekeeping system, you have to take into account the local gravitational field, because general relativity rears its head again. Clocks at different altitude are going to have different time dilation. And you have to be aware of the local gravity in order to actually keep these clocks on time. More evidence for general relativity. So cool. So say you're doing a science experiment and you have a gas and you want to measure the temperature of that gas. You stick a thermistor in it, and it's a resistor that will change its resistance based on the temperature. So in order to actually get a temperature, you have to put a voltage across that resistor and measure the voltage. And a voltage is a time-dependent quantity. So you sample that voltage with some sort of atomic clock, and the more accurate the clock is, the more accurate the voltage reading will be, which means the more accurate the resistance reading will be, which means you can more accurately measure the temperature. When you improve clocks, you improve everything else. Atomic clocks. Also, think of things like LIGO. Like, you have this giant interferometer, you're making measurements all across the world. You need to come up with a standard time measuring the same event. Otherwise, your data is gonna be totally useless. You need atomic clocks to do literally any physics experiment. We're in the future, and it's crazy exciting. So that was my list, the top 10 things that physicists have done in the last 70 years. Let me know if I missed anything egregious. That was just my favorites. Leave your favorite in the comment below. But I want to end this list with another list. I just have 3 things. The first thing I want to say is that I think some people are going to have an opinion of like, well, NASA put a robot on Mars, and that's an engineering feat and not a physics feat. But like, get off my back, all right? NASA is a physics organization. MRI's medical, but medical physics. The computer simulations were, of course, physics, but that's because computer science hadn't been developed yet. Of course, if something in computer science happened now, I would say that was a computer science joint. That one's a physics joint. Deal with it. It's not like I'm saying CRISPR is a physics achievement because you had to know about the van der Waals force and physical chemistry. No, these are all pretty solid. These are all solidly physics. The second thing I want to say is that when people feel like they haven't lived through like amazing physics things, I do think it's because physics is just very, very slow. It takes a long time to get practical applications from like these huge discoveries. If you think the laser, that came out and people were probably like, okay, you have a collimated beam of light, who gives a shit? And it's not until like 15 years later when you're at the grocery store and you see someone with a scanner gun and they scan a thing instead of typing it into a calculator, and you're like, holy shit, lasers. Right? It takes time. So if you feel like something hasn't happened in the last decade, it's probably because we haven't seen the fruit of that yet. Although, guys, the black hole picture was like 4 years ago. That was it's so recent. But I do understand this sentiment. And I would argue that it's not because physics is stagnant. It's because physics is moving so fast. There are so many things happening all the time that it's not making the news like it would in the 1920s. And the very last thing I want to say is that I get it, okay? I understand that when someone says physics has not done anything in 70 years, they're not actually saying physics hasn't done anything in 70 years. They are saying, I have not lived through a giant paradigm shift in physics The standard model must be a failure because it doesn't have gravity. Physics hasn't done anything because there hasn't been like an Einstein relativity moment in my lifetime. I want a theory of everything. Why haven't you given it to me? I want it. Which is weird to me. I mean, yes, a theory of everything would be interesting. It would probably be pretty to look at, but it doesn't actually have to exist. Nobody said it had to exist. There doesn't have to be a theory of everything. There might not be. And that's fine. Actually, physics doesn't have to be beautiful. Maybe there is a beautiful theory of everything that we will never get to and we will never achieve it. But like, we have the standard model, we have general relativity, we have the BCS theory of superconductivity. It's all been pretty solid and good. Can you imagine if instead of doing all the things that I just talked about, everybody stopped and it's just like, we're all gonna do high energy theory, particle physics, nothing else until we solve this quantum gravity situation? Because like, I mean, no, I wanna do other stuff. Like, we have gravity, it's fine. It's fine over there, it's fine. We have done so much in so many fields, and it seems like a certain fraction of people are just like, but I want a theory of everything. And, you know, of course I blame all the airport books who said, oh, a theory of everything is coming very soon, because most physicists are like, it doesn't matter. It doesn't matter if there's a theory of everything. Like, we're doing all this stuff. We're making so much progress. We're doing so many things all the time. We don't need a theory of everything. Maybe there's not one. And I also get that if I was talking to this person in real life and someone said to me, physics hasn't done anything in 70 years. And I said, what? Lasers. Lasers. Do you know about lasers? Oh my God, have you seen a laser? Are lasers new for you? Because we should go look at a laser. We have so many lasers, just we can go touch one. It's fine. They're not going to say, oh, lasers count. Oh, I didn't think about lasers. They're just going to be like, well, I want a theory of everything. So yeah, this is just for the people, the other people, the people who like a big list of cool physics stuff. This was a fun list to make. It was a fun video to make. I love physics. It's really nice to see all these things like stacked together like a little sandwich of like, look at how amazing physics has been in the last 70 years. They used to cut you open and now you can just get an MRI, guys. We're in the future. Holy shit. So I realize the people who are like, physics hasn't done anything, are just repeating a statement that they have heard from like a podcast or a YouTube video from someone who's like, the physics establishment is out to get me, blah, blah, blah. And that's lame. That sucks. They go on and they do their little preaching about how like they've lost their way. They're just gonna build a bigger particle collider, I swear. You just wait, they're gonna do it. That's definitely a thing people have been talking about doing. Or they're talking about like, no one's doing the theory of everything. And I wrote a paper and it's on the archive, quantum loops, boop-a-doo. But I have a prediction, because I don't think they're gonna be talking about that anymore, because it's kind of lost. It's like no one's building a particle collider anymore. So you can't complain. Like, maybe they'll update the LHC, but they're not, no country is gonna build, no. Like, of course people talk about it, but they're not actually, no. It's not, no. And I think the theory of everything as like a thing has kind of like, we're doing fine without it, all the things. Like, I mean, people still work on it, and that's great, and that's fine. But like, it doesn't make as much sense for like someone to be like, I have a theory of everything. And it's like, bro, you've been saying that for 22 years. Where is it? No, you don't. So my prediction is that all of these like famous physicists, but really they're just YouTubers. Is that me now? Should I write a book about my prediction of what they're going to talk about next? My prediction is that all of these people pivot niches. They're going to go from theories of everything, and particle physicists are real bad, actually, ? And they're going to talk about AI, consciousness. Obviously, physicists belong in the consciousness discussion, not like, you know, neuroscientists or whatever. That's my expectation. My friend's a librarian and she gets all the pre-releases, and I saw this book and I knew this is where they're all going. You just wait. That's my prediction. A year from now, theory of everything videos are gone, and now it's like AI, consciousness, quantum. If I could end on a piece of advice, if someone is telling you that an entire field is broken and they're saying nothing has happened in 70 years, you could just Google it. But also, are they also selling you a book? Are they also asking you to listen to their podcast ads and buy a Casper mattress? They're just selling you a lie. And I don't get it. So... I want to take you on a thought journey, and I don't know if it's going to track, so let me know in the comments below. But do you remember 15 years ago when everybody was super into zombies and zombie apocalypses? And people would imagine the scenario where they are one of the few lone survivors of the zombie apocalypse, and now they're the leader of a group of people or something. And it's a fun thing to imagine for some people, I guess. I never really got it. I was always okay, it's the zombie apocalypse. I'm at a gas station. I see a man hobbling over. I would just be oh my gosh, this man is hurt. And I would get out of my car and I would be calling 911 and they wouldn't answer because it's a zombie apocalypse. And I would walk over and I'd be are you okay? And then a zombie, right away. Day one of the zombie apocalypse. I am obviously a zombie. There were lots of think pieces at the time about how people had these fantasies about apocalypses because they would finally show the world their value. And you're an IT professional and people are annoyed when you ask them if they turned it off and turned it back on again, and they lie to you and say they did, and then you have to walk to their office and you turn it off. It's a whole thing. And you're but in the zombie apocalypse, I would be the person that knows how to hook the solar panel generator to the water pump for the well, and we'd all have water, and then I'd be the hero. That type of thing. That mindset of the zombie apocalypse, I kind of see it in the people who watch these losers pretend that physics is broken. Once the physics establishment has an apocalypse and all the physicists are murdered in the streets, that podcast guy, that guy topples the physics establishment, and now he's the supreme physics guy. And since all the physicists are dead, the only people who can be the smartest in the room now are the people who knew all along, the people who watched the Joe Rogan podcast and know more physics than everybody else because they predicted it in advance. Did that track? That's the same scenario. The people who think that they would not only survive the zombie apocalypse, but they would be a leader, are the people who the physics podcasts. That's the same thing. Let me know in the comments below. Would you survive the physics apocalypse? Like and subscribe.